Here's our next section where we're going to be applying some mathematics. You're going to need writing utensil, your ruler, and you'll also need a calculator for this as well for the lens-mirror formula. Lens-mirror formula is a very simple and beautiful formula that will enable you to calculate a missing feature from the system. So I want to go ahead and share with you what the formula is. And it's involving the focal point, the distance of the image, and the distance of the object. So here's the formula. You have 1 over the focal length is going to be equal to 1 over the distance of the image plus 1 over the distance of the object. So imagine a scenario where you're given the distance of the object is equal to 10.4 centimeters. You're given the the height of the object is going to be 3.0 centimeters. The focal length is going to be equal to 3.6 centimeters. Question is, what is the distance of the image? Meaning, where is the image going to appear? And also, how tall will that image be? So, we have the distance of the object. We also have the focal length right here. So we can rearrange this formula and solve for distance of the image. So if we subtract 1 over DO from both sides, so we have 1 over the focal point equals 1 over distance of the image plus 1 over the distance of the object. If we subtract from both sides, we'll be able to solve for the distance of the image. So I'm going to put this over on this side. The inverse of the distance of the image will equal, those cancel over there, the inverse of the focal point minus the inverse of the distance of the object. And for this, you can use your calculator very, very easily. Okay, so I want to do the inverse of the focal point. So 1 divided by 3.6, I'm going to press enter, minus, and I'm going to be putting it in parentheses, the inverse of the distance of the object. 1 divided by 10.4. That gives me a decimal answer, a very, very small number. But remember, this is 1 over the distance of the image. This is the inverse of that. So what I'm going to do to both sides is I'm going to do the inverse of both sides of the equation now, and I can take the inverse of the answer, and that will give me the distance of the image will equal 5.5 centimeters. So that is where the image will appear, at about 5.5 centimeters. So we've solved for this. How do we solve for the height of the image? For this, we need to look at the magnification formulas. There's 2 formulas for magnification. So here's magnification. So magnification is lowercase m, and it's going to be equal to the height of the image divided by the height of the object. Okay, so let's look at this formula. Meaning, if my image is larger compared to my original, let's say it's twice as large. Let's say my image is 4 centimeters when the original object was 2 centimeters. That means my magnification is a factor of 2. 4 divided by 2 is 2. It's 2 times as larger. So that's one of the formulas for magnification. But there's another formula that you can calculate the magnification by using the distances. The magnification is equal to the negative distance of the image divided by the distance of the object. Since both of these equal m, we can actually set them equal to each other. So we set equal to each other. So the magnification formula becomes this: the height of the image over the height of the object will equal the negative distance of the image over distance of the object. I call it hi-ho, negative di-do. So let's go ahead and calculate. We've already calculated the distance of the image. Let's go ahead and calculate the height of this. This is what we're trying to solve for right here. Let's go ahead and, this is our master formula up here. So we're going to put that in a box. We're going to put this in a box and not disturb that. We can go ahead and rewrite this over here. We have hi-ho equals negative di-do. We're trying to solve for the height of the image. So we're going to multiply both sides by ho. If we multiply both sides by ho, we get this. The height of the image is going to be equal to negative. My distance of my image has been calculated at 5.5 divided by the distance of the object, which has been given to us, 10.4 centimeters, times the height of the object, which is given to us at 3.0 centimeters. So when we multiply negative 5.5 times 3.0 divided by 10.4, this gives us negative 1.6. So the height of my image is negative 1.6 centimeters. What does this mean that the height is going to be negative? That means it's going to be inverted. And if it's inverted, what type of image is it going to be? Is it going to be real or is it going to be virtual? The answer to that is it is going to be a real image. So let's go ahead and calculate the magnification of this. We calculated the height. Let's calculate the magnification, which is the height of the image over the height of the object. Okay, so the magnification equals the height of the image over the height of the object. We just calculated this, and it is a negative 1.6 centimeters, and the height of the object is 10.4 centimeters. So if I take a negative 1.6 and divide it by 10.4, this gives me negative 0.15. No units because the centimeters are going to cancel each other out. What does this mean? Well, I have two features about this number that I need to take a look at. I need to take a look at the sign, and I need to take a look at the size or the magnitude. If I have a positive magnification, that means my image is going to be upright or erect. If I have a negative magnification, that means the image is going to be inverted. That's the sign. How about the magnitude? Well, notice how this is actually less than 1. We can create a little scale here for magnification. Okay, we're going to start off at 0, And we're going to be going to +1 and to -1. Okay? If the height of the image is equal to the height of the object, my magnification is the same number divided by the same number, meaning that it's going to be 1. So this is going to be the same size. If it's a magnification of 1, it's going to be the same size. So here it's the same size. Here it also is the same size. However, +1, positive is going to indicate that it's going to be erect. Negative numbers are going to be indicating that it's going to be inverted. Well, what if my height of my image is 4, the height of the object is 2, and my magnification is 2? That means my image is going to be larger. So if the number is larger than 1, your object is going to be larger. If it's less than 1, in this zone here, it's going to be smaller. And the same thing here. If it's a -2, it means it got magnified. It's going to be larger, but inverted. If it's less than 1 like it is here, that means the object is inverted and it's going to be smaller than the original. So this number of magnification tells you whether it's going to be inverted and also if it's going to be larger or smaller than the original. So what I'd like you to do is to draw this, and we're going to create our own principal axis like this. If you can draw this going across, and if you can create your line that's perpendicular to the axis like this. Okay, if you want to put in this dotted line like this, this is showing that we are experiencing a concave mirror. Let's go ahead and draw in our features now. My object is going to be 10.4 centimeters away, and it's going to be try to be very precise about this, as precise as possible, because the more precise you are with these measurements, the better your drawing will be. So here is the distance of the object. My object is 3 centimeters high. So here's my object. Here's the height of the object at 3 centimeters. My focal point is 3.6 centimeters. So we measure 3.6 centimeters away from the principal axis, conjunction with this perpendicular. This is where the mirror is, the center of the mirror. And so I'm going to put a dot there, and that's going to be my focal point. The focal length is 3.6 centimeters from that mirror. Now that we have these, we can go ahead and draw what this would look like. And following our similar rules, rays of light that are going to be coming into the mirror parallel to the principal axis are going to exit through, you guessed it, the focal point. So we draw that line going there. That's the reflected ray that's coming out. And rays of light that go into the focal point are going to exit out, you guessed it, parallel. So where our rays converge, which is right here, that is where my image is going to be. Notice how my image is inverted. It is upside down. Okay, so the distance of my image is going to be from here to here. What's the distance of this? This is 5.5. The distance of the image is equal to 5.5. Does that sound familiar? The distance of your image, which we had calculated with the lens mirror formula, is 5.5 centimeters. Okay, now, what is the height of this? Okay, for me, I got -1 and I got 6 millimeters. It's -1.6. Height of the image is equal to -1.6. The negative means, again, that it's inverted. Does the -1.6 sound familiar? That's what we used to calculate from the magnification formula. So the lens mirror formula is a beautiful formula for calculating where your image is going to be and what the height is going to be with the magnification formula as well.